Hello my dear students, welcome to today's lesson. Today I am going to discuss with you all the 17th lesson of your grade 10 science textbook. It is a chemistry lesson and the topic is rate of reactions. So in the previous lesson students, we discussed changes of matter. Under that we looked at the chemical changes which are called the reactions, chemical reactions. So you are very familiar with what reactions are. What happens there? We have the initial substances, those are the reactants, and the reactants are converted to new substances, those are the products. So when reactants are converted to products, we call it a chemical reaction. Now we saw in the lab we did a few activities. You were able to see, now say when a reaction takes place, there is evolving of gas. That leads to rate of fizzing. So there you were able to see some metals when reacted with dilute acids, the rate of fizzing was high. Whereas some metals, the rate of fizzing was slow. Some very slow. So like that, we saw reactions where they took place at different speeds. So there we just use the term fast, slow, medium, like that we just compared them qualitatively. But here we have a method of determining the rate of reaction. So to compare how fast the chemical reactions take place, we use the rate of reactions. Even in nature students, you all see so many things. Now you see the raw fruits. So let's say a mango, when it ripens, it becomes the fruit. So that takes few days or sometimes few weeks depending on the fruit. So that takes a certain amount of time. Whereas if you light a camphor, it starts burning very quickly. Ignite a candle, light a candle. So that also burns somewhat fast. If you take firewood, if you try to burn firewood, that burns a little more slower than the candle. So like that, you see different reactions, different chemical changes taking place in your environment, day-to-day life, but they take place at different rates. So that is where we need to understand the rate of reactions. So with that introduction students, I'll move on to the lesson. Rate of reactions. Under that, we will be defining what rate of reaction is. Then we will see how we can calculate rate of reaction. And most importantly, we will be discussing factors that affect the rate of reaction. Why these rates differ, or the factors that change this rate of reaction. That means the factors that affect the rate of reaction. That is also something you all know. Now, I am sure at home all of you all make either tea or fruit juice or some kind of fluid drink that you all drink. So, when you do that, when you put sugar into iced water, you put sugar into hot water sometimes, and you might have dissolved sugar in normal room temperature water. And you all know, when we put it into hot water, sugar dissolves very fast. Whereas in ice water, it takes a long time. Normal water, it dissolves within a certain time period. So there also you are experiencing something related to rate of reaction. So there what is the factor? Temperature. When the temperature changes, the way sugar or salt dissolves in water differs. So like that, there are factors that affect the rate of reaction. Now when I say sugar dissolves in water. That is not exactly a reaction because you dissolve sugar and you get the sugar solution. It's just the change in the physical state of the substance. But that is also affected by temperature. The same way, if you can remember magnesium. Now magnesium doesn't react with cold water. But when you heat the water, heat the boiling tube containing magnesium strips and water, you see the reaction taking place. So there of course it is a chemical change, and there when we increase the temperature, the tendency of magnesium to react with water increases or changes. So there is an effect of temperature. Like that, there are different factors that affect the rate of reaction. We will be discussing them one by one. So that is the introduction, students. Now I'll move on to the lesson. So the first one, the cause of most changes around us are chemical reactions. So this is what I told you all. Around us in the environment, in our day-to-day life, there are few physical changes, but a lot of chemical changes. So given below are some of those changes. In your textbook, students, those are given in a certain order. Here I have put the pictures relevant to those reactions. So I will discuss them according to this order. So something that is not shown here. Now for you all to get energy, what do? You eat food. And when you eat food, the food has to undergo digestion. You all are familiar with the digestive system of our body. So inside the digestive system, the food undergoes digestion. How long does it take? Now normally if let's assume you have your breakfast at 8 o'clock, say till around 12 or 1 o'clock in the afternoon, you really don't need to eat anything if you have a proper meal. Why is that? Because for the food to digest completely and for the nutrients to be absorbed by the body, it takes about 4 to 6 hours. So depending on what type of meal and what quantity you eat, it can slightly vary, but it takes a long time. So that is a somewhat slow reaction. So that is one reaction that you see in your day-to-day life or that you experience every day. So when we say chemical reactions, first one I will say digestion of food. Digestion of food. Then what is the first picture you see there in the figure? Cheese, yogurt. So how is cheese and yogurt produced? From milk. How long does it take? It takes about 1 or 2 days for the full procedure to complete. So that is also a reaction, a chemical change, because you initially have the milk, then you have the curd that is completely different from milk. So reactant and products. But that takes a longer time. So you see the production or manufacture of yogurt. So here I will say manufacture of yogurt. Manufacture of yogurt. Then this one, an example I told you all, burning firewood. Now firewood is hydrocarbons. There is carbon and hydrogen present in firewood. And when it burns, carbon dioxide and water vapor are produced. So that is a chemical reaction. So burning of firewood. Burning of firewood. Now burning of firewood, does it take place very quickly, very slowly or moderately? We can say moderately. Within a few hours, a stick of firewood will burn off. So that is somewhat slow reaction. Then this one, compared to the burning of firewood, look at this. Blast of a cracker. How long does that take? Few minutes. You light the cracker, it just sparkles or it just blast and you hear the sound. So that is very fast. So blast of cracker, that is also a chemical reaction. Blast of cracker. Then this one, you can see petrol or fuel being pumped into a car. There what happens? The fuel has to undergo combustion so that the engine can function. Ignition of petrol or diesel. How long does that take? As you put the key, you start the car, it starts working. So it's a very fast reaction. Within seconds, the reaction takes place. Ignition of petrol. Ignition of petrol. Then this one. What is that? Iron nails. Normally we use objects made up of iron. There are many different objects. Iron nails are one of those. When you get the iron nails, you see it as a grayish color, shiny metallic object. But with time, few months or sometimes it depends, few days, few weeks, few months, but it takes some time. You can see the rusting. So there are also iron is the reactant, then you know with oxygen and water, it forms rust. Rust is the product. So that is also a chemical reaction. Rusting of iron. Rusting of iron. Then what do we have? We have this one, something that we have seen in the lab. I have shown you all sodium reacting with water. We take a large trough of water, into that we put a tiny piece of sodium. Because it's a very violent reaction. You have seen the sodium darting on the surface of water. You would have heard the hissing sound because hydrogen is evolved, right? And I told you all, if we have a small amount of water, you can feel the beaker becoming hot. It has the possibility of exploding, the reaction, because it's so violent. So that is also a chemical reaction, and that you know is a very fast reaction. So sodium reacting with water. Sodium reacts with water. Then this one, again an example that I mentioned to you all before. What is that? Ripening of fruits. So like I said, either days or weeks are needed for the fruits to ripe. So here also you can see there are some fruits which are really ripe, some are raw, some are half ripe. So it takes a long period of time. So ripening of fruits. Ripening of fruits. Is that okay, students? Then there's one more that I have shown to you all. This is again something familiar to you. Can you see the metal pieces here? And although it's a colorless liquid, you all have seen the reaction of zinc with dilute hydrochloric acid or dilute sulfuric acid. So we can say reaction of zinc with a dilute acid. There you see the evolving of gas bubbles. So or effervescence or liberation of gas. So that is an observation that confirms that reaction is taking place. So zinc with dilute acids. Zinc with dilute acids. So that is a slow reaction or a fast reaction. It's over within a few minutes, maybe 10 to 15 minutes most, but depending on the size of the zinc you take and the amount of HCl, but it is somewhat fast reaction. So you have seen that. Then there are so many other reactions we observed. We took a piece of sodium, we cut it, we looked at the freshly cut surface, and while observing itself, the freshly cut surface tarnishes. So there, sodium reacts with oxygen in here. That is a very quick reaction. Whereas when you burn magnesium, you have to hold it to the flame. Again, it takes a few minutes for the magnesium strip to burn with a bright white flame. Whereas there are some other metals that do react with air, for example zinc. But you have to keep on heating it for a very long period of time, even for the color to change. So that takes a long time. That is a very slow reaction. So here we can say burning of magnesium. Burning of magnesium. I'll write the chemical symbol. So these are some of the examples that you are familiar with. In addition to this, you can think of so many other changes. Now when we cook food, you take a potato, you boil it. During boiling, there is a lot of change taking place. Even there will be a chemical change. So like that, there are so many changes that you observe in your day-to-day life. And there are some changes that we are familiar with. Now say for example, when nitrogen gas reacts with hydrogen gas, ammonia is produced. We have discussed that. So there it is carried out in the industry. So like that, there are so many reactions. So you are familiar with chemical reactions, and when I discussed all these reactions, I said it either takes place very fast, moderate speed, it takes few seconds, few minutes, say half an hour or 1 hour, 1 day, few days. Like that, we just refer to them saying that they can be either slow or fast. But you can't definitely say which is faster, which is slower. Now, if you remember when I said zinc with dilute acid, I said depending on the size of the zinc, it will be over within about 10 to 15 minutes. So, there I am not giving you a quantitative idea. Just qualitatively, I am saying, okay, this will be fast, this will be slow. So, it doesn't give a definite information about the rate of reaction. You are able to identify whether they are fast or slow, but you can't exactly compare and say this is faster than this is slower than this. So, that is why we need to consider the rate of reaction. So, with that introduction, students, we will move on to the next slide. So, here there is an assignment given in your textbook. Prepare a list of chemical changes, including the above changes, considering rates of chemical reactions that take place in those changes. Tabulate them as given below. So, they have given you a table. In that, you can see the first column, fast reactions. Second column, slow reactions. So, you will have to separate them out. So, if you remember, the first reaction I wrote was digestion of food. Is it fast or slow? It takes few hours. So, we can put it under slow reaction. Digestion of food. Then what was the other reaction? I will go back. Here you can see manufacture of yogurt, then burning of firewood. So, we will consider two reactions at a time. Manufacturing of yogurt. That again takes about 1 or 2 days. So, it's not a fast reaction. It takes time. So, there it is considered as a slow reaction. Manufacture of yogurt. Manufacture of yogurt. Then we had burning of firewood. Now, burning of firewood, is it fast or slow? Now, compared to blasting of crackers, burning of firewood is slow. But compared to these, what can you say? It is somewhat fast. But it takes a few hours for a splint of firewood to completely burn off. So, then it's better we put it under slow reactions. Now, can you all see the confusion? Now, in comparison to blasting of cracker, comparison to combustion of or ignition of petrol, burning of firewood is slow. But compared to digestion of food and manufacture of yogurt, burning of firewood is faster. So, there again we have the problem of dividing them, classifying them. But still we will put it under slow reaction. Burning of firewood. Burning of firewood. So, that is the reaction there. Then what are the other reactions? We saw the blast of cracker and ignition of petrol. That of course you are very sure they are fast reactions. Within seconds, ignition of petrol and blast of cracker. So, here ignition of petrol. Ignition of petrol. Then there is the blast of cracker. Okay. So, then what was the reaction? After that we had rusting of iron and sodium reacts with water. So, that is also something familiar to you all. Now, sodium reacting with water, how long does it take? Very fast reaction. So, that can be classified under fast reaction. Sodium reacting with with water. Then on this side, we will have the next reaction. One thing we saw, reaction of sodium with water and rusting of iron. Rusting of iron, it takes either days or months. It depends on the quality of iron. So there it is a slow reaction, rusting of iron. Rusting of iron. Thereafter, what was the reaction? Ripening of fruits, then zinc with dilute acid, burning of magnesium. So if you take those reactions, ripening of fruits, obviously it's a slow reaction. Again, days to weeks. So ripening of fruits. Ripening of fruits. Then on this side, we have the reaction of zinc with dilute acids, burning of magnesium. Those are very fast reactions, or fast reactions at least. So here we can say zinc with dilute acids. Then we can say burning of magnesium. So these are the reactions that we discussed before. What are the other reactions that you can think of? Sodium reacting with water, that also we have already written, burning of magnesium. How about reaction of magnesium with water, hot water? That is also a reaction. But compared to these, burning of magnesium, reaction of magnesium with water, that is slow. But compared to these reactions, it is faster. So where can we put that? We can put it under fast reactions. So when we say fast also, there is a difference in their speed. So here, we can say magnesium with hot water. That is a fast reaction, magnesium with hot water. Now let's say when we heat copper, zinc, copper, when we heat it strongly for a prolonged period of time, then only you see the color of the metal tarnishing, the shine being lost. So that is a very, very slow reaction. Even iron with dilute hydrochloric acid. When I did the activity in the lab, you were able to observe that it took a very long time before even a bubble of gas was liberated. So that's also a very slow reaction. So here we can say copper heated in air. So that is a very slow reaction. So now we have classified some of these reactions, students. Still you might be thinking, why can't we put this burning of firewood with fast reactions? Because it happens within hours. Yes, it depends on how you consider fast and slow. So even when we did the activity in the labs, we said no. Now magnesium, zinc, aluminium, they evolve gas bubbles fast when reacting with dilute hydrochloric acid. Whereas iron, we said slow reaction, and copper never reacts. And then we took the three metals. If you take zinc, aluminium and magnesium, there is a difference. You were able to observe that. So again, they can be categorized as fast and slow reaction. So this is based on comparison only. We don't have a definite value to show this is fast, this is slow. And there is no definite criteria as to how we can classify them based on just our observation. So this method of saying fast and slow reactions is not very, very useful. Especially when it comes to science, chemistry, we need to have a quantitative value. so that we can confirm and say that this is a fast reaction, this is a slow reaction, this occurs faster. So for that purpose, we need to have the rate of reaction. So this lesson is on rate of reaction. Can you all understand that clearly? I'm sure you can. So with that, I'll move on to the next slide. So here you can see the speeds of various chemical reactions vary. So that's obvious, no? We saw in the previous slide so many different reactions. The speeds are different. Reactions like ripening of fruits, digestion of food and rusting of iron are slow. So there we use the term slow. And they are also, when you compare digestion of food, that is fast compared to ripening of fruit. Ripening of fruit is fast compared to rusting of iron. So it depends. Again, relative terms. But combustion of petrol, reacting zinc with dilute acid and blasting of a cracker are comparatively fast. So comparatively fast. It's a comparative term. Comparatively fast. Accordingly, some reactions are instantaneous reactions. Instant reactions or rapid. Now say sodium being exposed to air, instantly it starts tarnishing. Now when petrol is ignited, instantly it ignites, it starts burning. So those are very rapid, fast or instantaneous reactions. While some others are very slow. So like rusting, ripening of fruits, all those are very slow. There are reactions that take place in a second, in a minute, in an hour, and during several days, and during several months, or even during several years. So it can be seconds, minutes, hours, days, months, years. So from the reactions that we looked at also, ignition of petrol, reaction of sodium, you can usually put it under seconds or even minutes. That also again see, we can't really confirm. It's very fast, seconds or minutes. Then hours, digestion of food. Days, ripening of fruits. Sometime months, we can say rusting of iron. Good quality iron doesn't rust very quickly. It takes a long time. So there are so many reactions like that. Takes months and several years. Now for example, you all know carbon. Carbon is diamond is one allotropic form. Graphite is another allotropic form. How do they form? The fossil carbon. What is the fossil carbon? When living organisms die from the dead plant and animal bodies, they undergo chemical changes on the earth crust, under the soil, under the required suitable conditions. They get decomposed and get converted to either crude oil, petroleum crude oil, fossil fuel. Then also they can be converted to graphite as well as diamond. Does this happen in a day or two? No. It takes many years. Even petrol, diesel, all these are produced by chemical reactions. So they are very slow reactions. So like that, we have fast reactions, slow reactions. Compared to a reaction that takes place in 2-3 hours, a reaction that takes place in months is slow. But compared to a reaction that takes place within minutes, a reaction takes place in 5 hours is slow. So based on what type of reactions we are comparing, the slow and fast nature will change. So as I said before, students, again, we need to have a definite way to express this rate of reaction. Otherwise, it will depend from person to person, or depend from even us, depending on how we consider, look at the reaction, we will say one is fast, one is slow. So because of that, we need to define rate of reaction. I am sure you all can understand that concept clearly. So with that, I will move on to the next slide. So when a chemical reaction occurs, reactants are used up and new products are formed. This can be easily understood by considering the following reaction. So, you are familiar with these, students. Now, let's say we have calcium carbonate reacting with dilute hydrochloric acid. Now, what is this? This is a reactant. Hydrochloric acid is another reactant. Now, you have calcium carbonate. You have seen it can be either calcium carbonate chips or it is calcium carbonate powder. So, either way, this is a solid substance. Then, hydrochloric acid, it is a colorless solution. And when they react together, they form calcium chloride, then water, and evolve carbon dioxide. Now, in this, again calcium chloride dissolves in water, so you get the calcium chloride solution. Water, you know, is a colorless liquid and carbon dioxide is a gas. So, in this, how can you observe that the reaction is taking place? You either see the solid, the white color solid, either powder or chips or pieces, dissolving in hydrochloric acid, or you see the disappearance of the reactants, or the reactants are being used up. So, when we say disappear or dissolving, they are reacting. So, that means the reactants are being used up. So, reactants are used up, then what happens? You get a colorless solution, calcium chloride solution, but you see the fizzing or evolving of carbon dioxide, evolving of CO2, or what we call as fizzing. So, fizzing of carbon dioxide means carbon dioxide is a product. So, there what is happening? The products are being produced or formed. So, here reactants are used up, products are formed. So, always when a reaction is taking place, reactants are used up and products are formed. And when these are visible to us, we know that the reaction is taking place. So, either by observing the reactants being used up or products being formed, we know that the reaction takes place. So, for that we have discussed before. Effervescence or evolving of a gas, then temperature change, the beaker becoming warm or cold, then there can be a color change, they can burn with a colored flame. So, like that, there are so many changes. Formation of a precipitate, all these tell us that there is a reaction taking place. So, now we want to observe the rate of reaction. So, for that, if I go back, here again, we will take the same reaction, calcium carbonate plus HCl giving rise to calcium chloride plus water plus CO2. Now, we will need to, initially I did not check whether the reaction was balanced. I just wanted to explain it to you all. If we check calcium 1, carbon 1 carbon. There are 3 oxygen atoms. 1 hydrogen, 1 chlorine here. But here there are 2 chlorines and 2 hydrogens. So, very easy. If we put a 2 there, a coefficient of 2, then the reaction is balanced. So, in this, these 2 are the reactants and these 3 are products. So, again to recall what you have learned before, reactants can be either elements or compounds or a combination of elements and compounds, as well as the products again can be one or more than one. That also can be element, compounds or elements and compounds. So, in this, of course, all the substances, reactants and products, all of them are compounds. Calcium carbonate, hydrochloric acid, calcium chloride, water, carbon dioxide, all are compounds. So, the reactants are converted to products. So, that is a chemical reaction. Now, the rate of this reaction can be determined by the speed of loss of reactants or by the speed of formation of products. So, here we need to know the speed at which the reactants are lost or the speed of formation of products. So, here you can see the calcium carbonate disappearing, and also you can observe carbon dioxide evolving. Both of them can be seen. But we select a factor that is more easily observable. Now, it's very difficult to observe the calcium carbonate dissolving. You see it's dissolving, but with time, you can't really say, okay, this much dissolve, like that. You can't quantitatively measure. Because as you put calcium carbonate, you pour HCl, we have seen that when we collect carbon dioxide gas, it keeps on reacting. But we can collect the carbon dioxide gas. We have done that before. Downward displacement of water or upward displacement of air. So, either way, we can collect carbon dioxide gas. So, it's easy to observe. You can observe the volume of carbon dioxide collected in a unit time. So, we can calculate the speed of formation of carbon dioxide. So, speed of formation of products. When we say speed, normally we relate the change with time. That is what speed is. So, the speed of evolving of carbon dioxide. So, you can collect carbon dioxide and you can calculate the volume of carbon dioxide evolved in a unit time. So, that is the speed of carbon dioxide evolving or speed of formation of products. So, like that, depending on the reaction, we can either calculate the speed of loss of reactants or speed of formation of products. So, then, what is observable easily in this reaction is the rate of disappearance of calcium carbonate or the rate of evolution of carbon dioxide. Which is more easy? I just told you all. It is more easier to observe the rate of evolution of carbon dioxide. This is more easily observable. So, the rate of evolution of carbon dioxide can be observed easily. So, we can easily calculate the rate of reaction based on that. Is that clear, students? So, then I will move on to the next slide. Rate of reaction is the amount of change occurred in a unit time. So, in the previous slide, I explained to you all, when the reaction is taking place, reactants are used up, products are formed. So, the speed at which reactants are used up or the speed at which products are formed, will they be different or the same? It's going to be the same. Why? Because the reactants are the ones that are going to be converted to products. So, the rate of reactants being used up and the rate at which the products are formed will be equal, and that will be the rate of reaction. So, speed of reactants being used up, speed of products being formed. They are going to be equal for a particular reaction, and that is going to be the speed of reaction, which we will call as rate of reaction. So, that is how we get this definition. So, this is an important definition, students. You all have to know this. Rate of reaction is the amount of change occurred in a unit time. Rate of reaction is the amount of change occurred in a unit time. So, when we say change, that is the reactants being used up or the products being formed. So, based on that, we can define rate of reaction. To do that, we can use two equations. One is rate of reaction equals amount of reactants used up divided by time taken. So always I said, if it is a rate, if it is a speed, we always consider it for a unit time. So that is why amount of reactants used up in a unit time. So to find that, we divide it by time. So here you can see rate of reaction is the amount of change. So the amount of change is amount of reactants used up. Occurred in a unit time. So we divide it by time taken. Is that clear? So this is same as the second equation that I am going to write. So here you can say is equal to here rate of reaction so amount of reactants used up or amount of products formed. So here we can say amount of products formed. That also has to be in a unit time. So we write it as time taken. So rate of reaction, amount of products formed divided by time taken. Is that clear to you all? So always remember students, when there is a reaction, there are reactants, they are being converted to products. That is the reaction, and this reaction occurs with a certain rate or occurs at a certain rate. Now this rate is the same when you calculate the amount of reactants used up or the amount of products formed in a unit time. So that is what we call as the change occurred in a unit time. You have to remember that because the reactants are the ones that are going to become products. Say for example, if we have magnesium burning in oxygen, magnesium oxide is being formed. Now you have seen this taking place. We hold the strip of magnesium to the Bunsen flame. It takes a few minutes for it to ignite. Once it starts, you have seen the strip burning. From the bottom, it keeps on burning. As it burns, you can see the size of magnesium decreasing and the magnesium oxide increasing. So, as the reactants are used up, the products are formed. So, the rate at which reactants are used up is equal to the rate at which the products are formed. And that is the rate of reaction. Is that clear to you all? So, this is what we will be using to measure and compare reactions. To compare the rate of reactions in a quantitative manner, we will use the rate of reaction. So, here students, I discuss the definition. What is rate of reaction? Rate of reaction is the amount of change occurred in a unit time. And that can be defined as rate of reaction, that is amount of reactants used up, time taken. And if it is rate of reaction, amount of products formed, time taken. So, for example, if they tell you to calculate. Now say example. So, as an example, if we consider the reaction students, just for example, I have not weighed or measured anything, but just assume if there is 20 grams of magnesium strip and for that to burn completely, we'll just say it takes 2 minutes. Then, if you are to calculate the rate of reaction. Now here for us, it's easy to weigh the strip of magnesium. You can also weigh the magnesium oxide formed after the reaction is complete. That's also fine. But initially, we have weighed the mass of magnesium. So that is 20 grams. So then you can calculate the rate of reaction based on the amount of reactants used up in a unit time. So here amount of reactant used up. Here students, because I want to write everything in one slide, I am writing it below. But when you all write it in your book, when you all write this as an answer, you can write this whole thing as one sentence in one line. Amount of reactant used up divided by the time taken. So here, now you know 20 grams of magnesium reacts in 2 minutes. So then, if you calculate, you get the rate as 10 gram per minute. So like this, depending on what we measure. Now here it is the reactant 20 grams in 2 minutes. So the unit for rate of reaction here is grams per minute. Like this. Now let's say consider the previous reaction where we saw calcium carbonate, another example. Where you have calcium carbonate reacting with hydrochloric acid, I will consider only this product. There are other products but carbon dioxide. Because I said there you can observe calcium carbonate dissolving, but better if we can collect carbon dioxide. So let's say if we collect 100 centimeter cubes of carbon dioxide, let's say it takes about 5 minutes. This is just an example, students. It all depends on how you take calcium carbonate, what the temperature is. This is just to show you all how we can calculate rate of reaction. So, 100 centimeter cube was collected in 5 minutes. So, here if you want to calculate the rate of reaction. What is that going to be? Amount of product formed divided by time taken. So here we can calculate it as 100 centimeter cube divided by 5 minutes. So that is going to be 20 centimeter cube per minute. Centimeter cubes per minute. So since we measured the volume, then it is going to be 20 centimeter cube per minute. So these are different ways in which we can calculate the rate of reaction. So can you all understand that? I am sure you can. So if we quickly go back, you have to remember these three, students. The definition for rate of reaction is the amount of change occurred in a unit time, and the equation, either first one or the second one. Rate of reaction, amount of reactants used up divided by time taken, or rate of reaction, amount of products formed divided by time taken. And always for a certain reaction, these two are equal. Why? When the reactants are used up only, the products are formed. So they occur at the same rate, that is the rate of reaction. So based on that only, we saw that we can calculate the rate of reaction. So depending on what we calculate, we can have different units. That's what I wanted you all to know. It can be grams per minute, it can be centimeter cubes per minute, or it can be something per second, or it can be something per hour. Again, depending on the rate of reaction, whether it's a very fast reaction or whether it's a slow reaction. I'm sure you all can understand that clearly. So with that, students, I will move on to the next slide. So there are two ways to determine the rate of reaction. Already I calculated the two ways. Now in the first one, I showed you all the reactants being used up, amount of magnesium that was used up. Then we saw the amount of products being formed. That again, I divided by time there. So when you have a set of reactions, now say you have a set of reaction where you have different sizes of magnesium strip and the same amount of hydrochloric acid. If you want to compare the rates of those reactions, then it can be done in two ways. One way, you can fix the time and you can measure the amount of reactants used up or the amount of products formed within that particular time period. So, we will consider the two ways first, then I will explain both the methods. So, there are two ways to determine the rate of reaction. First one, the amount of reactants used up or products formed in a given period of time. Given period of time. That is one. Now, if we consider this, I will give you all an example. Let's say we have 3 test tubes. Into that we have dilute hydrochloric acid, all equal volume, the same solution is taken, and into this, to this one we put a piece of magnesium, to this one we put a piece of zinc, and to this one we put a piece of iron. The metals are different. Now you know all these 3 metals will react with dilute hydrochloric acid. We have seen magnesium and zinc are fast reactions. Iron is a slow reaction. But now we want to compare it properly. Compare the rate of reactions. So here what does it say? The amount of reactants used up or products formed in a given period of time. So here if I take the products, you know when a metal reacts with dilute acid, what is the product? The salt of metal. So here it will be the metal chloride and dissolving of hydrogen gas. So like we discussed before, we can easily collect hydrogen. So here H2 gas is a product and it can be collected easily. So what can we do? We take equal sizes of magnesium, zinc and iron. Then we take the same amount of HCl. We can do it one after the other, or we can do all 3 at a time if you all are doing it in a group. The main thing is we need to collect the hydrogen gas evolved. But here, amount of products formed in a given period of time. So what we need to do is, we need to fix the time. So we will say, collect H2 gas for 5 minutes. So we have fixed the time there in a given period of time. It can be 5 minutes, 2 minutes, 15 minutes, 30 minutes. If it's a very slow reaction, we can even consider it as 1 hour. So depending on the reaction. But only thing is, we fix the time in a given time. So the hydrogen evolved by the strip of magnesium in 5 minutes. Hydrogen gas evolved by zinc when reacted with hydrochloric acid in 5 minutes. And the amount of hydrogen evolved when iron reacts with hydrochloric acid. That also in 5 minutes. So the time is the same. The volume of gas that was evolved will be different. So let's say if we take magnesium and zinc, maybe magnesium there will be about 50 centimeter cubes of hydrogen gas. This is again students, I am just giving you all a quantity, just the value, just to compare and show you all how we can calculate and compare the rate of reaction. So let's say magnesium 50 centimeter cube, zinc about 45 centimeter cube, whereas iron is only 5 centimeter cube. Now just by looking at this itself, you know, because time is the same, more hydrogen is evolved by magnesium, slightly less amount is evolved by zinc, whereas this one, iron, only a very small amount. So immediately you know the rate of reaction of magnesium with dilute HCl is high. Rate of reaction of zinc with dilute HCl is somewhat less. But whereas rate of reaction of iron with HCl is very slow. So we can compare these very easily. So to do that, how do we calculate rate of reaction? Rate of reaction, amount of product formed, time taken. So here, since the time is the same, you don't even have to divide. But if you divide, you will get the value easily. So you can understand. So for magnesium, 50 centimeter cube divided by 5 minutes. For zinc, 45 centimeter cube divided by 5 minutes. And for iron, 5 centimeter cube divided by 5 minutes. So here you can see 10 centimeter cube per minute, 9 centimeter cube per minute, and this is only 1 centimeter cube per minute. Here again students, these are not values obtained from an activity. This is just for you all to understand. So I have used random values. Maybe this can be even a little bit more faster when compared to iron, because you saw when we did the activity, magnesium and zinc were very much fast, almost look like the same rate of fizzing. So there you have to understand. This is just to compare. So from these also now you can confirm and say, now this is 10, this is 9, that is 1. So there is a big difference between these two and iron. So now you can understand why the rate of reaction, calculating rate of reaction is very important. So this is the first method where we have the time constant, but we look at the change within a given period of time. So here I have taken the formation of product. It can be the reactants being used up also within a unit time or within a given time period. Is that clear to you all? So that is the first method. Then we have the second method. We can say second method, time taken for a given amount of reactants to be consumed or a given amount of products to be formed. So here we fix the amount of reactants used up or the amount of products formed. Then we measure the time taken. So here the factor that is going to change is the time taken. amount of the reactant or the amount of product is going to be fixed. So again, as an example, let's say reaction of calcium carbonate with hydrochloric acid. Now here we are going to measure the time taken. Let's say now I have told you all calcium carbonate is available as chips and it is available as powder. So here in both the reactions, the reactants are calcium carbonate and hydrochloric acid, calcium chloride, water and carbon dioxide will be evolved. We can either collect the carbon dioxide gas or we can consider this calcium carbonate. So what I will do is I will consider the reactant here. So again, when we do the activity, what we can do is I have a conical flask. Into that, I take calcium carbonate chips. Then here, I take calcium carbonate powder. And to that, I put equal volume of HCl. Into both, we put equal volume of HCl. Now what do? We have a given amount of substance. Now then, calcium carbonate chips and calcium carbonate powder should be of equal amount. So let's say we take 10 grams of calcium carbonate chips and 10 grams of calcium carbonate powder. So a fixed amount of the reactant, but we will measure the time taken. So let's say for both of these to react completely, we will say this takes about 5 minutes. For the 10 grams of calcium carbonate powder to completely react with this hydrochloric acid, it takes 5 minutes. For the evolving of carbon dioxide to stop completely, it's 5 minutes. And this one, calcium carbonate chips, we will say it takes about 15 minutes. So immediately by looking at the time, you know which is faster. When we use calcium carbonate powder, it's going to be fast. When we have calcium carbonate chips, it's going to be slow. So this is like I have told you all before, when you have a large substance or when you have tiny pieces, that has an effect on the rate of reaction. We will be discussing this as a factor that affects the rate of reaction. For now, I want you all to understand the two methods of calculating the rate of reaction. So here also we can calculate rate of reaction. So what is it here? Rate of reaction equals amount of reactant used divided by time taken. So then, you can see here 10 grams of calcium carbonate, that is for chips, divided by 15 minutes. So there you can see 2/3 grams per minute. Whereas for powder, it's 10 grams divided by 5 minutes. That is going to be 2 grams per minute. Now if I calculate this also, this will be about 0.6 grams per minute. So when you look at the two, you know which is fast, which is slow. So here we can confirm and say. That is the important thing. So can you all understand the two methods now? We can have the reactant or product constant. We can fix a value, a fixed amount of substance and measure the time. or we can have the time fixed and measure the amount of reactants used up or the products formed. So those are the two ways in which we can measure and calculate the rate of reaction. Is that clear to you all? So with that, students, I am going to end this chapter, and in the next chapter I will discuss the factors affecting rate of reaction.